everyone. Good afternoon, everyone. Welcome back to Math 122. So today we're going to be studying, or reviewing, I guess, for the exam, which is coming up on this coming Tuesday. Okay, so you have today, Friday, Saturday, Sunday, and Monday to study. It's going to be in class, 75 minutes. I have it written already. It's the same exact length as the last exam in terms of like number of questions. So it's like 3.5 pages of questions, basically. 35 points, and it covers sections 2.3 or 2.2 or something like that up to 5.1. So there is one question on there on tangent lines. There is a question on there about Riemann sums. So those are the two freebies that I'm going to give you and let you know that those two questions are on the exam. Other than that, all of the questions come directly from the homework assignments. So as long as you know how to do all of the homework problems, you know how to do all the exam problems too. And yes, I'll make all the numbers work out nicely so that you don't need a calculator on the exam. Maybe I should say something about my office hours between now and then. So I will have office hours from 10 to 12 on Tuesday. So if you want to study with me on the day of the exam, before the exam, you can do that. I'll be in the Math Tutoring Center. Other than that, you're going to have to go to the Math Tutoring Center and meet with someone else, or you can meet with Jacob. I don't see Jacob today, but he'll send out an email with like a special review, okay? So keep your eyes peeled for your email, or if you're in the group me or whatever you guys have, then you can do that. Someone asked me about opening multiple sections at once on Wiley. I was able to do it okay. I can show you how I did it. I don't know if that's helpful. But, I mean, I'm not sure what exactly, if you're wanting to have, like, all of them open at once, but if you open the homeworks like so, like in other tabs, then you can open each assignment and it'll open another tab. So you can float between the assignments like that. I'm not sure if that is what you were wanting to be able to do. Who was asking me about that? So you... tab switching?
Yeah, like if you could honestly just put all the questions in like one homework and just like label it like or something.
Yeah, I did try to do that because I was like, maybe they just wanted it all in one assignment. It won't let me like add in all of the questions. So short of me like writing down every single question and then checking every single box from every single thing, which would take me like an hour and a half, I can't. So sorry. Is that okay?
Yeah, I was just
all right. Then yeah, so I thought maybe it just literally wouldn't let you open like multiple assignments at the same time, and I was like, yeah, that would suck, but okay. Any other questions, like administrative questions, before we review? Okay, then what I'll do is, I know some of you already have questions, but first I want to go back and tell you what each section was about, and that maybe will help you to remember what it is that you don't remember and you want to talk about. So, where is my Chapter 2 notes? Am I crazy? I can't even find my Chapter... oh, there they are. Chapter 2 notes. Okay, so Chapter 2, what do we do in 2.2? Okay, so Chapter 2, we were still kind of just talking about, like, what is the derivative? Well, it's the instantaneous rate of change. So a lot of the problems from Chapter 2 have to do with checking graphs, understanding what the graph of a derivative is doing, understanding how the graph of a derivative can tell you something about what the function is doing. And that connection was really just that, look, the derivative tells us what is the slope of the function at a given point, right? So increasing, decreasing, concave up, concave down, Leibniz notation, the units of the derivative, tangent line approximation. What else? And then, okay, using those for, okay, concavity is also in there. So second derivative, positive, negative. How to make the graph of a function whose first, second derivative satisfy certain properties. Concavity with tables. Okay, and then finally it was like applying all the chapter 2 concepts to like cost, revenue, and profit, basically. And then we had chapter 3. So chapter 3 was all about how to do derivatives. So in chapter 3, the first thing we learned was like a bunch of derivative rules for constants, linear functions, sum and difference, constant times a function. The power rule was a big one, right? And then we learned some more rules, like derivative of a to the x, derivative of e to the x, or e to the kx, and derivative of the natural log function. We also learned the product rule. Oh, the chain rule. Okay, that was a big one, the chain rule. And then we learned the product rule and the quotient rule. Okay, so all of these rules should be something that you have memorized going into the exam. If you don't have them memorized yet, well, there's no better time than right now to memorize them. Except maybe several weeks ago. That could be a better time. Chapter 4 is here. So what was chapter 4 about? Chapter 4 was all about, okay, now we have this derivative thing. What is it good for? Well, it's good for telling where our function has a local minimum or a local maximum, i.e. where is the function hitting peaks and valleys, right? So we defined local mins, local maxes. We defined what is a critical point. We have a critical point anywhere that the derivative is 0. Doesn't necessarily mean that we have a max or a min at that point, but it could be a candidate for a max or a min. To figure out whether it is or not, we used either the first derivative test or the second derivative test. But you have to be a little bit careful because the second derivative test can fail sometimes, okay? So what was next? Well, we did a lot of min-maxing, and then we did inflection points. So where does the second derivative change sign? Okay, so an inflection point looks like this. It happens, well, we have a candidate for an inflection point if the second derivative is 0. But as we saw in our most recent quiz, just because the second derivative is 0 doesn't necessarily mean that we have an inflection point, okay? We could have a situation where we have like an x to the 4 situation where it goes from positive concavity to 0 briefly and then to positive concavity again. That can happen, in which case we wouldn't have an inflection point. So it's where the concavity changes. And global max and min, okay, the only difference here is we don't really actually need the first and second derivative test. We just find all the critical points, find all the boundary points, and we put them in a table and we check, okay, what is the value of the function at the critical points and the boundary points, and you just look for the biggest and the smallest number. That's how you find global mins and maxes, okay? So between inflection points, critical points, classifying local mins, maxes, and then finding global mins and maxes, we have a lot of these points, which sometimes we're taking these points and we're plugging them either into the function, or we're plugging them into the first derivative, or we're plugging them into the second derivative. And like the number one mistake that I see on quizzes and on homeworks and people asking questions about this in office hours are people have trouble determining when they should be plugging into the function versus the derivative versus the second derivative, okay? So that's something to keep in mind. I'm going to get to your question in a sec, Jake. And then finally, we had chapter 5, where the only thing that's going to be on chapter 5 is Riemann sums. So we have left Riemann sums, we have right Riemann sums. Remember that a left-hand Riemann sum will be an underestimate if the function is increasing, but it'll be an overestimate if the function is decreasing. Okay, so which one is an over or an underestimate depends on whether your function is going up or down, right? So here's a depiction of that. And that's what we learned, and that's what's going to be on the second exam. So, Jake, what was your question? Mm-hmm.
Does it have to, so you don't have to put those numbers?
Great question. So the question is, for a global min and max problem, do I have to use the first derivative test or the second derivative test to classify the critical points as minimums or maximums? Can anyone answer that question? When I'm doing global min and max, do I need to use the first derivative test or the second derivative test? Who says no? Is that you, Olivia? Can you say why not? A little bit?
Well, I would use it for the critical points.
Okay.
But the other stuff, you don't have to, because you can just plug it into the original function. The largest number and the smallest number.
Yeah. So notice, like when we did this example, we found the critical points and we put them in this table with the boundary points. And then what did we do? We actually didn't classify the critical points, which the critical points were 8 and -2. We did not classify them as minimums or maximums. We just put them in the table, and I said, well, look, I don't care if they're mins or maxes. They're one of those two, or maybe neither. But what I'm really looking for is the lowest point on this function. So let me draw a picture to help illustrate that. So imagine that you're looking for like the mins and maxes of a function like from, I don't know, -3, what is that? Not -3, how about 3 up to 10, yeah? So what do? Well, you say, I know that the global minimum and the global maximum are going to occur at either the boundary points, here, or possibly at a critical point, which it looks like we have 2 critical points, here and here, because that's where the derivative is 0. So, in order to find the global max, we say the global max is gonna be at one of these 4 points. Yeah? I actually don't care whether or not those critical points are local maximums or local minimums, because all I'm trying to answer is the question of which point is tallest, which is not a question about whether it's a local max or a local min. It's just, look, we take all the places where we could have a local max and all the places where we could have a local min, throw in the boundary points, and then we have a list of all of the places where we might get the global max. So if we just find the value of the function at each of these 4 points, then I don't really need to use the first derivative test to say, oh, well, this one is a local minimum. I know that it could be a local minimum, but I only really care about, well, is it smaller than the other 3 points? Does that answer your question? That's a good question. All right, was there anything else that people wanted to ask, like, about what we just discussed before we move into, like, you know, just general student questions? All right, if not, then we'll just open it up. So who's got a question? Yeah, Olivia.
I was having a hard time with the 5.1 homework.
Okay.
Tomorrow, so
Sure, so let me pull it up. Do you have one in particular that you want to do?
I think it was a lot of the like estimation stuff.
Okay, using Riemann sums and stuff?
Yeah, and then when it gets into like giving me a graph or something like that, like I'm actually a table. I don't really remember.
Okay, you want to do this one?
Yeah, that was.
Okay, let me copy the table into okay. So we have 0, 14, 28, 42, and 56 are the inputs, and then the outputs are 17, 30, 1072, 641, 366, and 235. And this is T, and this is R of T, where R of T is the rate in cases per day. Of COVID cases, and T is measured in days. And it says, assuming the rate was decreasing. Okay, assuming that R is decreasing, find a lower and upper estimate. For total COVID cases from T equals 0 to T equals 56. Okay, so this is a super standard Riemann sum problem. Okay, so let me just make a couple of comments before we start. So the first thing they tell us is that the rate is decreasing, okay? So that's going to help us infer whether we should use a left sum or a right sum for a lower or upper estimate, okay? So every time that I have students who struggle with these tables, which is almost all of my students in all of the times that I have taught this course, I recommend drawing a picture, okay? Because I find students have a much easier time when they have the picture, okay? So let's draw what this function could look like. And our picture doesn't have to be perfect. It just should give us an idea of what we're doing. So at time 0, we have lots of cases per day, and then we have less and less and less cases per day as we go along. So this function could look like the following. I'm going to go 14, 28, 42, and 56 here. And I know that the function, generally speaking, is going down. Yeah, generally speaking, it's going down. And I don't actually know how fast it's going down, but I don't really care. I'm just trying to see the picture of what does this function look like generally. Okay, so, and now I should ask myself, what am I actually trying to do? It says, find a lower and upper estimate for the total COVID cases from T equals 0 to T equals 56. Let's translate that into what it means for this graph. What it says is, since this height is representing the rate at which something changes, we learned in class that the area under a rate curve will give us the total change in that quantity, right? In other words, the total number of COVID cases from T equals 0 to T equals 56 is represented by the area under this curve, which is shown in red. And it tells us to estimate this area, okay? So we are going to estimate this area, which the tool we have for estimating the area under a curve is the Riemann sum, specifically the left and the right Riemann sum. So, someone help me out. Is the left Riemann sum or the right Riemann sum gonna be an underestimate? Okay, a right-hand sum is going to be an underestimate because for a right-hand sum, we choose the height of the first rectangle to be that of the height of the function on the right side of the first subinterval. And then we're going to draw our rectangle like shown, okay? So it's going to be an underestimate if the function is decreasing, because for a function to be decreasing, that's the same as saying, look, the height of the function on the right side is less than the height of the function on the left side. That's what it means for a function to be decreasing. Okay? So the height on the right is lower for a decreasing function, which is why it's an underestimate to use a right sum. Okay, so by the way, I think it's critical, one critical reason why you should draw this picture is because it's going to help you determine what is your n, i.e. your number of rectangles, right? I find a lot of students see this table, and when I ask them, how many rectangles are we going to use? The first thought that everyone has is, we have 5 data points, so we should have 5 rectangles, right? But it's actually not the case. We have 5 data points, yes, but what we're counting is not the number of data points we have, but rather the number of gaps between data that we have, okay? Which is 4. So we're going to use 4 rectangles for this one. So another way of thinking about that is to say, we're not going to count the number of data points. Instead, we're going to count the number of dividers between data points, okay? Which in this case is 4. So we need 4 total rectangles. So the picture of the right-hand sum is going to look like this. And then we just have to determine what are the areas of these rectangles. Well, we know that each rectangle is 14 units wide. So I can represent the area of these 4 rectangles as 14 times the height of the function on the right side of the first subinterval is f of 14. And then we would add 14 times the height of the second rectangle is the height of the function at 28, so f of 28. And then plus 14 times f of 42. And then plus 14 times f of 56. Which in this case would be 14 times 1072 plus f of 28 is 641 plus 366 plus 235. And you can pull the 14 out because each of these has 14 in it, so we just factor that out. Okay, so that's for an underestimate. Or a lower estimate, whatever. Any questions on this so far? How are you feeling? Good? Happy with this? Okay. Then let's do the upper estimate. So to do the upper estimate, since this is a decreasing function, the upper estimate is going to be given when I do a left-hand sum. So my rectangles will look like this instead. And then like this. And then like this. And then like this. So again, I can't recommend enough that you should draw the picture of what you're trying to do. And not just rely on the formula and the table, because I think a lot of students would be tempted to include, 14 times f of 0 in this sum, which we shouldn't, because for the pink sum, there is no rectangle with that height. Okay? In fact, there should only be 4 rectangles. So if you do the drawing, and then you look at your sum, and you go, in my drawing, there's 4 rectangles, but in my sum, there's 5 things. Maybe that can give you an idea like, this isn't quite right. All right, so for the upper estimate, all we're going to change is we're going to do 14, and inside here I'm going to put the heights of the rectangles. So the first one has height f of 0. And the second one has height f of 14. The next one has height f of 28. And then the last one has f of 42. Which is 14 times, whatever those numbers are. 1730 plus 1072 plus 641 plus 366. All right. So that's the full story of this problem. It comes down to a handful of different things. First and foremost, you have to determine how many rectangles you're going to use and how wide is each rectangle going to be. That's done far more easily, in my opinion, if you draw the picture. Second thing we need to know is, depending on whether our function's increasing or decreasing, the right or the left Riemann sum will be a potentially lower or possibly upper estimate of the true area under the curve. Okay? Lastly, we need to understand that just in general, the area underneath a curve which describes something's rate of change will tell us the total change in that quantity. Beyond that, it's just geometry. It's not even hard geometry, it's just rectangles, right? Finding the area of rectangles. So that's pretty much the whole story on this one. Are there questions about any of that? So, a trick for remembering this, what's going to be a lower and upper estimate, well, first of all, I would say just don't try to use a trick. Just draw a function that's decreasing, and then you'll see immediately that if you do a right-hand sum, it's going to be an underestimate, right? You just see that straight away. So you could just always draw this thing to see that, or what you could do is you can put the association like decreasing, underestimate is a right-hand sum. And then you just know that, okay, if it's increasing, then underestimate is going to be a left, right? So you really only need to remember one of these, because then you've also got decreasing, over, left, and then you've got increasing, under, over, right. But really you only have to remember one of them in order to be able to infer what the others are. So that could be something to put on a flashcard if you don't like drawing pictures. All right, final questions on this before we move on to the next topic? All right, I think that handles Riemann sums. So let's move on to a different topic. So who's got another question? I saw Braden first.
I'm still kind of struggling with
e to the kt, so doing derivatives involving e to the kt?
Yeah, that's the only one that I have a problem with.
Okay. Do you have a specific problem in mind, or you want me to find one?
I have one, it's on 3.2.
Okay, can you read it out for me?
If $1,500 is deposited into a bank account that pays 2% interest, compounded continuously.
Okay.
The balance fee after 2 years is B equals F of T equals 1,500 e to the point 0.022.
Okay, that's true.
And then it says find F prime of T.
Is that it?
And then it also says find F of 10 and F prime of 10.
Okay, well, we know how to plug, right? So really the main part of this is finding the derivative of a function like this. Okay, so there's two rules that I'm going to use to do this derivative. The first rule tells me what is going to happen with this 1500 when we do this derivative. I have 1500 times e to the 0.02t. Question for the class. Do I need to use the product rule? Do I need to use the product rule for 1500 times e to the 0.02t? I'm seeing no. Head shaking no, and I agree. We don't need to use the product rule. Can someone put it into words? Why not? Why do I not need to use the product rule to handle that 1500? Or what should I do instead? Well, we can't use the power rule for this one. I mean, there's a way in which your answer could be correct. Yeah, you could use the power rule. If you use the power rule, it would become 0, right? In other words, the constant multiple rule says if you have a number times a function, okay, we learned that if you have a number times a function and you do the derivative, it's the same as just doing the derivative of the function and then multiplying by that number. So when we do the derivative here, the 1500 is just going to hang out. And then in this blank, I'm going to write down what is the derivative of e to the 0.02t. Okay? So maybe this is making it more complicated than it needs to be, but let's see what is the other rule that I'm going to use. The other rule I'm going to use is the fact that the derivative of e to the kx, who knows the right-hand side of this rule? Drew, you got it? Exactly, it's k times e to the kx. So what is k in my situation? It's 0.02. Okay, so I have e to the 0.02t, so I'm going to put in 0.02 for k in the right-hand side of this rule, and that would look like this. 0.02, and now I still need e to the 0.02t. Okay? So you could then go ahead and multiply these two numbers together, and whatever you get, okay, is your final answer, right? Make sense?
Yeah.
So I think what you need to remember for this one is mainly this rule, right? E to the kx, you do the derivative, it's whatever is the number, okay? Whatever that number is just comes down, and then you just rewrite the whole thing, right? You just rewrite e to the 0.02t again. The only thing is you multiply by whatever that power is, okay? All right, so just one final comment on this. I find there's a strong desire when people see f of x equals e to the 6x. There's a strong desire for some students to write that this is then going to be, well, the derivative of this, of course, should be 6 e to the 6x minus 1, right? So this is actually not correct for the following reason. The power rule, okay, the power rule says that the derivative of x to the n is n times x to the n minus 1, okay? So in this situation, we can't use the power rule because we have a number being raised to a variable. That's different from the power rule in which we have a variable being raised to a number, okay? So that's the difference of that and why we can't use the power rule for these types of derivatives. Are there any other questions on this one? All right, then next question I think was Dan.
Yeah, on 4.3, 4.4, question 4.
All right, let me pull it up. So 4.3, 4.4. You said question 4? Aha. Yeah, this was a good one, wasn't it? Okay, so sum of 3 numbers is 36. Each number is greater than or equal to 0. One number is twice that of another. Find maximum product. All right. So this is the basic premise of the problem. So this problem is fairly challenging. I think the reason that so many students find this problem challenging is you have to do some sort of abstract reasoning. So this is kind of a problem where the underlying mathematical question is obscured in some sense. So we're going to start by taking this problem and formulating a rigorous mathematical question in terms of what we've studied in our class so far, okay? And that's sort of a difficult task, but let's work our way through it. So what do we say? We have 3 numbers. The only problem is I don't know what any of the numbers are. The only thing I know is that they're all bigger than 0. One of them is twice the other, and they sum to 36, right? So what are my 3 numbers? Let's call the 3 numbers x, y, and z. Okay, and since I could call y z or z y instead, we can go ahead and decide which 2 of them have this 2 times relationship. So I'm going to say that y is equal to 2 times x. Yeah? And then we also have that the sum of these numbers is 36, right? So in particular, x plus y plus z equals 36, yeah? And then besides that, we also have x larger than or equal to 0, y larger than or equal to 0, and z larger than or equal to 0. So now let's see what we're looking at. We want to say something about the function p equals x times y times z, right? We want to maximize the product of these 3 numbers, okay? But this is a univariate calculus class, not a multivariate calculus class. I don't know how to deal with functions of multiple variables. I know how to maximize and minimize functions of one variable. So I'm going to try to write this product all in terms of x. Okay, all in terms of x. Or if you wanted, you could write it all in terms of y or all in terms of z or whatever. Okay, so that's my goal right now. So to do that, I'm happy actually that I already know what y is in terms of x. I can just replace y by 2x, right? And in fact, if I use the fact that y is 2x and the fact that x plus y plus z is equal to 36, then I can find out what z is in terms of x by doing the following. So I'm going to replace y in this equation by 2x, and I get x plus 2x plus z is equal to 36. So that tells me that z is equal to 36 minus 3x. So now between x, and I know what y is twice x, and then z is 36 minus 3x. So now I can rewrite P as the product of x times 2x times 36 minus 3x. Okay, so now this is looking better than it was before, because we've translated a 3-variable function into a 1-variable function. I know how to use calculus to find the max or min of a 1-variable function, right? Okay, so now let me comment on one other bright red flag that we see in this problem, okay? The bright red flag that I see is in the problem. What do we see here? This word right here, the, okay? They say we want to find the maximum value, okay? Well, I have a function which is a cubic polynomial, right? It's a cubic polynomial with a negative coefficient on the cubic term, which means that this function looks like this. And it's asking me for the maximum. Well, there is no maximum of a cubic function unless you specify the domain, okay? Which it turns out the domain is specified, okay? Because we have these 3 conditions that all 3 of these numbers must be positive, okay? So if we rewrite all of these inequalities in terms of x, we get the following. We have x is larger than or equal to 0. 2x is larger than or equal to 0, which, by the way, is equivalent to the first condition because that would mean that x is larger than or equal to 0 if you divide both sides by 2. And then finally, we have 36 minus 3x is larger than or equal to 0, which, if you move 3x to the other side, gives us 36 is larger than or equal to 3x, and therefore 12 is larger than or equal to x. So now we have our domain, which says we're trying to do basically the following. Find the global max of P of x equals x times 2x times 36 minus 3x on the interval from 0 to 12. And this is a problem that I think we should all, at least by come Tuesday, we should all feel comfortable solving a problem like this. Yeah? So, kind of, I don't want to say a lot of work, but a non-zero amount of work went into deciphering the problem and writing it down in terms of what it is actually asking us to do, right? So, that's a skill that is just something that you work up over time, okay? It takes practice for these sorts of problems. But are there any questions up to now on how we got to here? Do we feel like this is really hard? Who thinks this is really hard? It's okay, don't be shy. Okay, yeah, I think it's kind of tough. But once we get to here, let's go ahead and finish this off, right? So we still have to find out what is the global max of this function on this interval. So to do that, let me ask you all a question. Am I going to need to use the first derivative test or the second derivative test for this problem? No. Andon says no. Why not? You're right. Yeah, for a global max problem, what are we going to do? We're going to find the critical points. We're going to find the boundary points, and we're going to plug in and see which is the biggest. All right, so let's do it. So we need to find the critical points. To do that, we're going to take P' and set it equal to 0. So to do that, I need to find out what P' is. Well, I can multiply this whole thing out to get, what, 2x squared times 36 minus 3x, which becomes 72x squared minus 6x cubed, right? And that's p, so I want to take p prime, so p prime equals, what, 144x minus 18x squared. Okay, and we set it equal to 0. So divide both sides by 18. I think 18 goes into 144, right? What is it, like 8?
Yeah.
It's 8. X minus x squared equals 0. And then we can factor the left-hand side as x times 8 minus x is equal to 0, and therefore x is either equal to 0 or x is equal to 8. So these are my critical points. So to find a global max, all I'm going to do is I'm going to take this function and I'm going to make my table of x values. And on my table, I am going to put both of my critical points and also the boundary points. But one of the critical points actually is a boundary point, namely x equals 0. So I'm only going to list that once. So it's 0, 8, and 12 go on here. Now I have my critical points. I have my boundary points. What do I want to do with them? I want to plug them into what? The function's derivative, or the function's second derivative? What do we want to plug into in this one? The function itself, right? Because we're looking for the tallest point. The height of the function is given by when we plug into the function itself, right? We don't need the derivative or the second derivative for this problem. We're just going to plug in. So if I plug in 0, well, I'm going to get 0 because 0 times 2 times 0 times whatever, it doesn't matter what it is, it's going to be 0. And also if we plug in 12, we're going to get 0 because if you plug in 12 to this one, you get 36 minus 36, which is 0. So it's going to be 0. And then if you plug in 8, I don't know, you're going to get whatever that number is. What was it? 1536. So I would say this is our max product. Okay? So any questions on how we solved this one? All right, if not, then we'll just make use of all our time and move on to the next thing. So who's got one for me? Yeah, Andon.
Do you mind going over the quotient rule?
The quotient rule, absolutely. Yeah, no problem. So let's go back to that's chapter 3 merged. So that was in section 3.4, right? Okay, so what is the quotient rule? Basically, the quotient rule tells us how to find the derivative of one function divided by another function. So with all the rules, we want to understand, first of all, when should I use them, right? Well, we should use the quotient rule anytime that we see one function being divided by another. Like this would be a great example of a problem that we need to use the quotient rule on, because we see this huge fraction sign, and we have complicated stuff on top and bottom, right? So we should use the quotient rule, right? Or we could use the quotient rule for e to the 2t divided by t or something like that, right? So that's when we use it. And how do we use it? Well, the rule says you do the derivative of the top times regular bottom and then minus regular top times derivative of bottom, all divided by the bottom squared. So the way to remember that is people say low d high minus high d low over low squared. So that's one way people remember it. And I just want to mention that if you mix these two up, everything will be ruined. Okay, so I mean, not everything, but your problem, your solution to the problem will be ruined in the sense that you will get the negative of what you should be getting. So, actually, not even necessarily that. Oh, yes, you would get the negative of that. Yeah. So, anyways, the point is the order matters. Let's do a practice. So here's one. So the first thing that's telling me I should use the quotient rule is I see this huge denominator sign here, or this fraction sign, and I got a function in the denominator, I got a function in the numerator. What I'm going to do is I'm going to say, if you want to remember low d high minus high d low, you can, or you can remember that it's like f prime g minus f g prime, whatever. The first step that I would do is I would say, look, this is f of x over g of x, if you're doing f and g, or if you're doing high and low. Oh, I'm on the wrong one. I would say this is f over g, or if you want, you can call it high over low, whichever one floats your boat. All right, so what do I need? I need f prime, which is the same as d high, which is whatever is the derivative of the numerator, which in this case is 21x squared. And I'm also going to need g prime, which is d low, which is the derivative of the denominator, which in this case is 2x. And now what I need to do is 1 of f prime g minus f g prime all over g squared. If that's what you want to remember, great. If you want to remember low d high minus high d low all over low squared, that's fine too. But in either case, what are we going to do? We're going to replace f prime or d high by 21x squared. So it's going to go 21x squared times g, which is just our original denominator. Yeah, thanks. It should be x to the 6th. Right? 21x to the 6th. Thanks. And then minus. And now we need fg prime. So regular numerator, which is 3x to the 7, times the denominator of the bottom, which is 2x. And we take this whole thing and we divide it by x squared plus 1 quantity squared. And we can just leave it at that. If you want, you can simplify, but if the problem doesn't say fully simplify, why would you do more work than I ask you to, right? So that's quotient rule. How you can remember it, the two different formulas, and how to apply it for this one. How we feeling?
Yeah, I just need it.
Yeah, no problem. I'm just asking if that cleared everything up.
I forgot, like, which one was the F?
Yeah. It's, I mean, F on top and G on bottom is sort of like alphabetical, I guess, if you think like top to bottom. Yeah. You got a question, Jillian?
I know you said you can switch them. Like, could you do like f of x times g prime of x and then y is like prime of x times g of x?
So the question is, could you instead do f g prime minus f prime g all over g squared? Is that right?
Yeah.
So if you do it like this, what will happen is you'll get the negative of what you should get. And here's why. The reason is 5 minus 3 is not the same thing as 3 minus 5. Okay? The thing on the left is 2, and the thing on the right is minus 2, right? So if you mix up the order of the numerator for the quotient rule, you will get the same answer as you would normally, but negative. So it's sort of the opposite of the correct answer in terms of like the sign, right? So the one that the order doesn't matter for is the product rule. So order doesn't matter for the product rule. The reason that order doesn't matter for the product rule is because prime G. It's because although subtraction cannot be done in any order, so this is a no-no, addition can be done in any order. 5 plus 3 is the same as 3 plus 5. So it's okay to mix up the order for the product rule, but not for the quotient rule. Does that clear everything up? All right. Good question. Are there other questions related to this? All right, if not, I want to maximize the use of our time, so have we got another one that we want to discuss? Or just a topic is also fine. Sorry? Chain rule, absolutely. That's a good one to go over. I think a lot of students had a hard time with chain rule. And not just this class. All of my students, for all time, have always had a hard time with the chain rule. So let's go back over it. So the chain rule is, again, we want to say when we should use the chain rule, and then we'll learn how to do it. So the when we should do it is when we see a composition of functions, which we can tell that a composition is present when we see one function inside of another function. So that can look like a handful of things. It can look like one function that's being like raised to a power, okay? Or it could look like the natural log of a function, yeah? Where we see, these are the sort of really explicit cases where we can see that there's a whole function in between two parentheses. That's immediately screaming out as a composition. But here's one that's a little bit less obvious, is this one here. We also need to use the chain rule for this one. And you might say, well, there's no parentheses. That's true, but you could imagine a pair of parentheses here and here, in which case, anytime you see a function which is inside of a power, that's another way that we say a function is inside of another function, in the sense that it's inside of the power, okay? So that's the times that we should use the chain rule, and now let's see how we do it. So what we're supposed to do is identify what is the inner and outer function, okay? What is the inner and outer function? And then we apply the formula which says we're going to leave the inside alone at first, and just do the derivative of the outer function, and then we will multiply by the derivative of the inside function. So sometimes we call that chaining out by the derivative of the inside or something like that. So let's just do a bunch of examples of this one. I think I almost used up all the examples that there are, but let's try this one. So 4t squared plus 1, all raised to the 7th power. You could, if you want, FOIL this 7 times, and then you would have a polynomial that you could just use the power rule on. But it's not really that practical to FOIL 7 times when you're taking a 75-minute exam. So let's use the chain rule. So the first thing we need to do is write this as a composition f of g of x. So we need to identify what is the inside function and what is the outside function. The inside function in this case is just what's between the parentheses. So g of x is just going to be, or t, I guess. G of t is going to be 4t squared plus 1. And then what should the outer function be? What's being done to this function? It's being raised to the 7th power. So the outer function is just t to the 7. So from here we know that we're going to need the derivatives of these guys. So let's go ahead and find them. G prime is going to be 8t, and f prime is going to be 7 times t to the 6th. Yes? So before we get going on the derivative part, are there questions about how we identified, first of all, that this is a composition to begin with? Or are there questions about how do I figure out which one's the inside and which one's the outside? You feel okay? All right. Then from here, it's really just applying the formula, okay? So the chain rule will become infinitely easier once you memorize this formula. Because now you have all of the pieces, and you just need to plug them into each other in the way that they fit in this formula, right? So the first thing we need to do is write f prime where we use g as the input. So f prime is 7t to the 6, and I'm supposed to put 4t squared plus 1 in as the input in this function. So that would just look like replacing t by the function 4t squared plus 1, which would be 7 times 4t squared plus 1, all raised to the 6th power. And now I still have to do this last part, which is multiply times g prime, which g prime is 8t. So I multiply by 8t. Okay. So that's an example of a chain rule problem. Feel good about that? Any other questions on this example? Should we do one more chain rule? Okay. Yeah.
For this one, could we just, like, I guess make it shorter to the product rule and then just add the derivative of g? Because it'd be the same thing. Like you bring down 7.
What you mean power rule?
Or power, yeah.
Yeah, I mean, that's essentially what we did, right? So when we, quote unquote, did power rule was when we took the derivative of f, right? So yes, what you could do is skip this whole procedure of writing this crap out and do the following. And this is, just depends on how comfortable you are with the chain rule. What you can do is say, aha, I can see this as a composition of functions. I know for the composition of functions I got to use the chain rule, which means I'm going to leave all of this crap alone and just do the derivative of the outside function, and then I'm going to multiply times whatever is the derivative of the inside function, which is 8t, and call it a day. That's fine. But the entire process of what we just did is all under the hood there. It's just that you're not writing it all down. Are there any other questions on this example? All right, let's do another another chain rule. Geez, I guess there's only one chain rule that I haven't done. It's this one. So I have g of x is e to the minus x squared plus 17. So I'll do it the fast way first to satisfy Andon, and then we'll do it the slow way. So the fast way would be to say, well, I know immediately that the 17 is going to go away, right? And for the rest of it, I know I have e to the minus x squared. That's a composition where the inside function is minus x squared. So I know that in order to do this derivative, I have to leave the outside function, which is e to the z, alone. So this is just going to be e to the minus x squared. And then I have to multiply by the derivative of negative x squared, which is negative 2x. Okay, so that's the fast way. Okay? Let's do it the slow way now, because not everybody is ready for that yet. So the slow way would be to say, okay, I have a composition of functions here. I can tell it's a composition because I have a function inside of another function. I do know that the 17 is going to go away, so let's just focus on doing the derivative of e to the minus x squared. So I'm going to say that this e to the minus x squared is f of g of x. And now I need to determine what is the inside function. Well, the inside function is what's inside of the parentheses, which in this case is inside of the power, right? So g is negative x squared. And now I just need to figure out what f is. So to figure out what f is, I just once I know g, I ask myself, well, what function would I need to plug this into? Okay, what function would I need to plug this into in order to get e to that crap? Well, it's exactly e to the x. And then I would say, okay, now I just need g prime, which is negative 2x, and I need f prime, which the derivative of e to the x using the e to the kx rule would be 1 times e to the x, which is e to the x. So now I just need to do f prime of g of x and then multiply by g prime of x. And that means I need to take negative x squared and plug it in to e to the x. So that gives me e to the negative x squared. And then I need to multiply times negative 2x. So this codes with that. So long way versus short way. I'm curious, who prefers the short way to the long way? Okay, and we have some people who prefer the long way, yes? A couple of people? Okay. Yeah, I mean, if you go further in math, probably eventually you'll end up using the short way just because it's so much quicker. But the long way is very rigorous, and everything is very clear, and probably you're less likely to make a mistake. All right, so that's maybe all we should say about the chain rule. You know what we haven't talked about yet today is tangent lines. Should we do a tangent line problem? Okay. Let's do a tangent line problem, maybe with product rule. Let's see if we can find one. Okay, whatever. I'll just make one up. Find the tangent line to f of z equals z squared e to the minus z at x equals 3, z equals 3. Okay. So we're trying to find the tangent line to this function at z equals 3. So what are the two things that I need in order to make the equation of a line? The slope of that line, and one other thing.
Y-intercept.
Y-intercept or a point. Which the y-intercept is a point, right? So those are the two things I need. So the tangent line formula goes like the following. Well, in this case, I'm going to write it with z because they give us the variable z. Okay, so that's the only difference. It's going to be f of a, right? F of a plus f prime of a times z minus a. Okay, so that's the formula. So in order to do this problem, I need to identify what is a, which it immediately tells us what a is. It tells us a is equal to 3. And then I need to figure out what is f of a, which is 3. Well, that's given by just 3 squared e to the minus 3, which is 9 e to the minus 3. That was easy. And now for the hard part. I need to figure out what is f prime of 3. Well, to figure out f prime of 3, I need to be able to plug I need to be able to plug 3 into f prime, which should be written here, but it's not. So let's do it. What is f prime of z going to be? What rule do I need to use for this one? Product rule, where my two functions are z squared and e to the minus z. So for the product rule, what we do is the derivative of the one and not the other, and then the derivative of the other and not the one. Okay, so by that I mean first things first, I'm going to leave e to the minus z alone. And I'm just going to write 2z, which is the derivative of z squared, times e to the minus z. And then I'm going to add. And then I'm going to swap the roles. So for this one, I'm going to leave z squared alone. And then I'm going to multiply times the derivative of e to the minus z, which, what do I get when I do the derivative of e to the minus z? We use the e to the kx rule, right? Where k is equal to what? Minus 1. So the derivative would be k, which is negative 1 times e to the minus z. Okay? So that's 2z e to the minus z minus z squared e to the minus z. So to find f prime of 3, I just plug in 3, so I get 6 e to the minus 3 minus 9 e to the minus 3. Which, if you have 6 apples and you take away 9 apples, I have negative 3 apples. By combining like terms. So finally, we're ready to come up with the formula for the tangent line. It's just 9e to the minus 3 plus, actually minus 3e to the minus 3 times z minus 3. Okay, so that's how we get the formula for the tangent line for this problem. So the common mistake that I see a lot of students making, or two common mistakes. First of all, I see a lot of people doing the reverse of this, where they put the derivative first and then the function second. Okay, that's not correct. But that's an easy mistake to make. The other mistake that I see students make is by confusing what is our variable and what is our constant, okay? A, in this case, is just a number. It's given in the problem. It's just 3. Okay, so some students want to put a 3 where the z goes, and then they get a little confused. But remember, our final answer should be a function, so we should still have our variable in the function, right? All right, that's that one. We got time for like one more thing if it's quick. So do we want to do something else? Or any questions on this one? Yeah.
I'm just a little confused. Where does the, in the f comma 3, where does the negative 9 e? I know it equals.
So I'm plugging in 3 into this function here. So the 6 comes from 2 times 3 is 6. That's here, 2z. And then the 9 comes from doing z squared, which z is 3. So that becomes a minus 9. And then you plug in 3 here, and that becomes e to the minus 3. Is that clear? All right, we'll stop there for today.